तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have seen several methods of design and implementation of digital systems. First we need to define the system, then identify the parts required, then identify the control signals required, partition the system into architecture and a controller, and for the controller you do ASM and implement the ASM. There are several methods of implementing ASM. We had talked about ASM using multiplexers and flip flops. We talked about ASM using ROM or PLA and flip flops. See, in the when you have a digital system whose specifications may change a little bit, once you design the hardware, it is difficult to change it. You have to scrap the whole hardware and redo it all over again. Some sort of a programmability is desirable. ROM based implementation of digital systems, ROM based implementation of controllers for digital systems is very good in that sense. It is a programmable ROM by PROMs. ROM based, when you say ROM based, we mean PROM based, programmable read only memories, and PROMs being programmable devices is very good. But the problem with PROM based design is the table becomes extremely large. It is tedious. I may have, let us say, 5 or 6 inputs, but let us say about 10-12 states. 10-12 states means I need 4 flip flops, 7 or 8 inputs, 7 inputs, 8 inputs, let us say. And for every state I need to know the input correspond to each of these input, the status of each of these inputs. So my ROM table becomes extremely large. First of all, it is tedious to make a ROM table involving all the conditions for each of the input in each state, and secondly the size of the ROM becomes extremely large. So ROM based approach suffers from the tediousness of design and also because of the large size of ROM required for implementation. Of course, cost of ROM those days used to be very high, and that was one of the considerations. But today the size of memory is not at all a consideration because memory chips are available very cheap, cost per bit of memory is very low. But still, why do you want to have a system whose memory is very large compared to the when you can do it with a much smaller size memory. So, we go for another approach using the ROM, a programmable approach, because as I said the alternative programmable is hardwired. The hardwired approach lacks the flexibility. Programmable approach using PROMs has the flexibility, but PROM is not a very efficient implementation. So, we want to retain the programmability of the PROM and the cost effectiveness and the compactness of the non programmable approach. So, we have an approach called microprogrammed design. Microprogram design of when it is a digital system. I am not going to go into the details of the hardware, because we remember that we had partitioned a system of any system, any digital system, into a block called architecture or the functional block and a controller block, and we send signal from controller to architecture and got the signal back from architecture into controller. These are called commands, these are called status signals, these are more than one signal, and then they may have external inputs and outputs. This also can have external inputs and outputs. So, when I say digital system design, I am not going to go into all this again, because we have already seen all these things. Several examples also we have seen. When I say microprogram design of digital system, I am only going to concentrate on this block. Microprogram implementation of a controller of a digital system, and when you have a controller, you assume that an ASM is already written. A controller, start with a controller design, start with an ASM. ASM stands for algorithmic state machine, ASM chart, and I am not even going to tell you how to do that, because we have again seen many of those examples. What is an ASM chart, how do you draw it for a given controller, take into account the input output considerations of the controller. So, assuming that we have an ASM, instead of a multiplexer based approach, or instead of a gate based approach, or instead of a PLA based approach, or a PROM based approach, how are we going to do a microprogram based approach? So, the limitation, the discussion of today's lecture is limited to implementation of the ASM of a digital system using a microprogram approach. So, what is this microprogram? Why is it called microprogram? Again, because it is a programmability built in, that is why it is called microprogrammed. Why is it microprogram? Well, when you say program, you normally understand a computer program, high level program like C, or even in a microprocessor you talk of an instruction like assembly language programming. When you say add or subtract or multiply or load or store, these are instructions. So, when a program consists of all these instructions, it is called a program. But each of these instructions has to be carried out using several steps. Each step of this instruction execution is called a micro instruction. So, when you are talking of a digital implementation where the circuit goes from one state to the next state based on an input being available or not available, this intermediate step or a minor step which is required in order to carry out a major task is called a micro step, and that is why this approach is called a microprogrammed approach. Otherwise, it is nothing like a programmable approach. So, what does it mean? So, I have an ASM normally, a state, let us call this state S, and an input, let us say X, and in this state the circuit remains in this state and input x is tested. If the x is true, it goes to a state, we will call it S0, we will call it S1. If it is false, let us say it goes to S2. Each of these states can have inputs, outputs. If there is an output of a output in a state, yes, some state, what do? We write it inside the box. So let us say there is an output of P for this, Q for this, no output. When there is no output for a particular state in the ASM, you do not write anything inside the box. And you write the state variable here, the state, what is the representation of the state, binary representation of the state here in the left hand corner. Let us call this 0 0, 0 1, 1 0. This is only a section of this P, it can reach from some other place, from here it may go somewhere else, all that we are not interested in. We are interested in this slice of an ASM chart. When I say I have a microprogram implementation of an ASM chart, what do I mean is, I will consider what is the address norm, what is the state in which the circuit is, what is the input that is being considered in this state, what happens to the controller, control if the input is true, what happens to the control when the input is false, and in each of these states what is the output. These are all information we need in order to execute the ASM chart properly, the controller properly, to implement the controller properly, we need all this information. In a prompt based approach, what we will do is, we will say the present state, let us say present state is P, and say what is the input being tested, X, X0 what happens, next state, output, P, X is 0, next state is Q, I am not P, I am sorry, present state is S0, X is 0, it goes to S2, output is P, same as 0, X is 1, it goes to S1, and next state is this again P, and so forth. Now, as I have only one input, so X is 0 or 1, then I can go to S1 and start writing the table. But in practice, in a real system, there are several inputs. So when there are large number of inputs, all these inputs have to be given here. Supposing instead of one input X, as I said 7 or 8 inputs, 8 inputs, there will be all the 8 inputs have to be given here, X, Y, Z, whatever, P, Q, R, S, T. Each of these inputs is 0 or a 1, what is the next state? So the number of, for one input, I have to take 2 rows of the ROM table. 2 rows of the ROM entry are required for one variable. If there are 2 inputs, there will be 4 rows required. The number of rows in the ROM will depend on the number of inputs in the system. So, if there are 8 inputs, for example, for each input you will have 2 power 8, 256, like that for each state. Suppose there are 12 states. So, the number of rows in the ROM table will be 12 times 2 power 8, which is 256, and it becomes an enormous table. But most of the times in S0 state, only input of significance is X. There may be Y, Z and so many other inputs. These inputs are not considered in state S0, but because you have to give the complete table of what happens in state S0, when input X is equal to 0, Y is equal to 0, Z is equal to 0, all other inputs are 0, 0, 0, 0, And then what happens to the state S0 when x is equal to 1 and all the other states are 0, and then when x is equal to 0 and y is equal to 0 and all that. So, keep on writing it even though we do not have any significance of them. The only variable of interest in state S0 is x, which can be very easily written in 2 lines. But because I have more than one input, I need to complete a table. ROM is a truth table, remember that. The ROM table is nothing but the truth table of a system. In a truth table, I should give all possible input combinations, whether they exist or not, whether they are practical or not. If the system has 8 inputs, all the 8 inputs in all the conditions should be available for each of the states. That makes the table very, very large, and the ROM size very, very large. To make the table is cumbersome. So, in a microprogram approach, what I am going to do is I will replace this ROM table by what is known as a microprogram table. Where I will say the present state input to be tested, and if the input is true, what happens? Input is false, what happens? So, present state is S0, input tested is x. If x is true, it goes to S1. If s is false, it goes to S2. And what is the output in this state? P. I am going to replace for each condition to be tested. This condition to be tested are called qualifiers. So, name for it qualifier. Each qualifier to be tested will make only one row in the microprogram table. That means my memory will be much smaller now, because I have to implement this table. Earlier I had to implement this table, which is huge. Now I have to implement this table. So, to make the microprogram table is very simple. More than that, making it, to implement the microprogram table is also very simple. So, I am going to have a smaller size of the ROM, smaller size of the memory in a microprogram approach. So, let me tell you, let me explain this problem with a simple example. We will consider a table, we will consider some chart given like this. I have some chart with 4 states. To make it very simple, at the same time make it clear, I have chosen an example with only 4 states. Let us call these states S0, S1, S2, S3 as usual. And let us say there are only 2 inputs in this, the qualifiers. P and Q are the qualifiers, are the inputs. If P is true, it goes to S1, the circuit is from state S0, it goes to state S1. P is true, if P is false, it goes to state S2. From S2 to S3, there is an unconditional transition to S3. From S2, there is an unconditional transfer to S3. In S3, qualifier Q is tested. If the Q is false, it remains in S3. If Q is true, it goes to S0. So, very simple ASM. Just to tell you, to illustrate the method of microprogramming, the ASM chart for implementation. So, I have 4 states S0, S1, S2, S3. We will assign binary values 0, 0, 0, 1, 1, 0, 1, 1, natural binary sequence. there are two qualifiers P and Q, and let us call there are three inputs, so three outputs A, B and C. We will say there is an A, B and C. Output of S0 let us call it A, output of S1 B, output of S3 C, S2 has no output. So that means I have here a table with 4 states, two qualifiers, 3 outputs. How do you do a microprogrammed table out of this? Once you have a microprogram table, that table is implemented as a ROM, so it becomes a microprogrammable ROM. So instead of making a ROM table, we will make a ROM table again. Instead of making a generalized ROM table in straightforward ROM table, we will do a microprogram ROM table, that is all. Here I am going to have the following things. The circuit is going to be in one of the present states, so I will call this present address. This is the microprogrammed table. Microprogrammed ROM table. Present address, there are only 4 present addresses, 0, binary value 0001, 1011, or if you want to write in decimal 0123. Then I am going to have next the qualifier to be tested. The qualifier to be tested are P and Q. So I need an index. Which qualifier to be tested has to be given by names of a binary value. So qualifier index we will call it. What do you mean by qualifier index? Qualifier index will tell you which of the qualifiers is being tested in the current state we are considering. If you are considering state A, S0, qualifier tested is P. If you are in state S1, no qualifier is tested. In S2, no qualifier is tested. In S3, qualifier Q is tested. So we should have an index for that. So we will say P is equal to 0, Q is equal to 1. This is called the qualifier index. Qualifier index. Then if the qualifier is true, what happens? The qualifier is false, what happens? The qualifier is true, it goes to one state. The qualifier is false, it goes to another state. So I should have a true address and false address. TA, FA. TA stands for true address, or I can say true address instead of writing TA. And what are the outputs? Outputs can be again coded. There are only 3 and there are 3 outputs A, B, C. I can say output A is 0, 0, output B is 0, 1, output 0 is 1, 0, and 1, 1 does not exist, no output. Or I can say no output 0, 0. This is qualifier index. I can have an output index, no output, A is 0, 1, B is 1, 0, C is 1, 1. This is called output index. So my job is very simple. I am in the present address 0. I will write binary, even though everything has been done in decimal. In binary, I will write it in decimal to make life simple. So, or I can do it in binary, no problem. 0, 0 is the present address. qualifier is being tested in state A is P, which is having an index of 0. If it is true, it goes to 0 1, true address. If it is false, it goes, oh, this has to be false. Both cannot be true. This has to be false. If it is false, it goes to 1 0. And output index is A, which is 0 1. That is all this state is considered. Earlier, if it had been a ROM based approach, I would have written with A is equal to 0 0, if X is 0, P is 0, Q is 0, what happens? P 0, Q 1, what happens? P 1, Q 0, what happens? P 1, Q 1, what happens? I should have written 4 rows. I have now 4 rows, instead of 4 rows I am writing only 1 row. That is the simplification I am talking about, both in the design as well as in the hardware. That is very good. Then goes the present address 0 1. I will write it in the sequence, natural sequence. What is the qualifier being tested? In state S, we know no qualifier is tested, because it is, if a circuit is in state S1, it has to go to S0 no matter what. There is no qualifier to be tested. When there is no qualifier tested, I do not have an index for that, but what I can do is I can use any index. I can either test P or Q. So, I will put P is equal to 0 as the index to be tested. Only thing, make sure both for true address and false address you write 0 0. So, I write true address 0 0, false address 0 0. What I mean by this is, in S1, in circuit when it is in S1, we may have a qualifier, whether it is true or false, the address is going to be the 0 0, the next state. From B it goes to A, I mean from S1 it goes to S0, that means from 0 1 it goes to 0 0, from 0 1 it goes to 0 0, from 0 1 it goes to 0 0, irrespective of whether qualifier index is present or not present, qualifier is present or not present. And then the output is B, which is 1 0. Okay. Now, the next is state 1 0, present state S2, again no qualifier to be tested, and both cases it has to go to 1 1, and there is no output. Finally, I am in S3, which is 1 1. Qualifier tested is C, whose qualifier tested is Q, whose index is 1. If it is false, it goes to 1 1. With 2, it goes to 0 0. And the output of state S3 is C, which is 1 1. So, this completes my microprogrammed ROM table. I need to implement this in a ROM. I give the present address. As soon as I give the present address, it has to come up the qualifier index is 0. It has to give this value, it has to this give this value, it has to this give this value, and it will go to one of these things. So, what is the size of my ROM? Size of microprogram ROM this is my address, these are the outputs. So, 4 2 power 2 2 2 power 2, 2 address lines into 2 times the width of the ROM is 1 2 3 4 5 6 7 number of bits. I used 2 power 2 times 7 ROM. In a traditional ROM approach, this 4 states would have given 2 variables, there are 2 qualifiers and 3 outputs. If I had implemented this using a ROM, I will remove this portion and try to give you a traditional ROM based approach. Traditional ROM base. Four states will require 2 variables, 2 inputs, 2 qualifiers, that is my P and Q, the 2 state variables. Okay. So, it will give you me the output next state, and outputs. Output again can be coded. If I want, I can code it. So, output code, it can be coded to 2 bits. Size is 2 power 4 times 4 bits. Two power 4 times 4 is how much? 16 times 4, 64 bits. Here this 2 power 2 for 7, 2 power 2 is 4 times 7, 28 bits. You can see the difference. 2 power 2 is 4, 4 times 7, 28 bits is the size. 2 power 4 times 4, which is 16 times 4, 64 bits. This is only for 2 inputs. Remember, as the number of qualifiers increases, the address lines increases. The address line comes in the exponential. The size of the ROM is determined by the address line, exponential address line. Whereas, when I have more qualifiers, only the qualifier index is going to increase. So, even with a 2-bit example, I mean 2 qualifier example, I have shown you the size of the ROM is considerably small, but as the number of qualifiers, number of inputs increases, there is an exponential increase in the ROM size in the traditional approach, whereas in the microprogram approach it is only a linear increase. So, there is a lot of difference between a linear increase and an exponential increase, and an exponential increase is very soon will reach the very large size, which is unmanageable both in terms of design and cost. As I said, not only it is the cost and the size, it is also the programming inconvenience. To write a ROM table with so many inputs, it becomes nuisance, tedious. Now, what is the hardware? Now, of course, this is the hardware for the ROM based approach. What is the type of hardware for the microprogrammed approach? Hardware for the microprogram controller. I need to have a ROM, of course, which is where we are going to store the microprogram. It is called microprogrammed ROM. I will call it microprom because it is a microprogrammed ROM, microprom. Input address is given. In this case there are two address lines. This particular example, the size will vary from problem to problem depending on the number of states and the number of input qualifiers. Then you have the qualifier index given to a multiplexer. A qualifier index, the inputs are given qualifier index, we will call it n to make it simple. N is qualifier index. The qualifier index chooses the qualifier. The qualifiers are in this case P and Q. The qualifier index is given to a multiplexer which chooses between the two qualifiers P and Q, and the value of P and Q is given to the another multiplexer which is given the true address and the false address, true address. So, this true address I will call it TA, false address I will call it FA. So, address is false, it will select this, address is true, it will select this, and this becomes the address of this ROM for the next state. Given to D flip flops, Q of this, present address, next address, clock. And the output index go through a decoder, ABC, no output ABC. Crowded, all right, it began. Decoder, no output, A output, B output, C output. This is true address, so this has to be two lines, this has to be two lines. P and Q are qualifiers, value true or false, that is selected by this multiplexer, and this multiplexer gives the new address. Next address is also 2 bits, and that is stored by this. There are 2 D flip flops here, so 2 D flip flops. And given as the next address. So, there is this extra logic. This is the PROM, we have the flip flop, here we have the flip flops and the PROM, 2 bits, so 2 bits, no problem, and the output code has to be, here also you need the output code to be, here also you need the output code decoded. So, that part is also common. What is extra? Decoder, no output, ABC. What is extra is this, one multiplexer with n inputs and n control inputs and 2 power n inputs, and another multiplexer with 2 inputs, but it has to be series of multiplexers because there will be a 2 address. So, there will be 2 of this. This is 2 into 2 to 1 multiplexer, 2 numbers. This is 2 power n to 1 multiplexer. So, 2 to power n to 1 multiplexer, 2 to 1 multiplexer, 2 numbers, these are 2 extra things. On the other hand, I save the size of the RAM even for a 2 bit, as I said, even for a 1 qualifier, 2 qualifiers, size is less than half, and if it is going to be more qualifiers, the size is going to be enormously small at the cost of some extra multiplexers, but more important than that is the versatility, the programmability. I can do it very elegantly, it is an elegant design. So, this is the final circuit of the microprogram hardware for microprogram controller. And as I said, n is the qualifier index. TA for 2 address, FA for false address. Good, very nice, elegant design. We will have to see a practical example, we will see it next time. But before that, I want to tell you some more, one more thing. This 2 address and false address, 2 addresses I have to give for each line. The circuit is in present state. If qualifier is true, it goes here, if the qualifier is false, it goes here. So, 2 addresses. Even when there is no qualifier to be tested, I have to give a 2 address and false address, 2 fields, both the same. For example, this does not have a qualifier. In state 01, we do not have a qualifier, but still we put an artificial qualifier of 0 and give the true address as 0 and false address also 0. So, giving this an extra field of the false address can be removed. If I can make some minor changes, a minor change in my ASM, to make a minor change in my ASM, I can make one address as an increment of the previous address, that is 1 added to the previous address, and the other address is a different address. So, I can eliminate 1 2 address field at all, one field completely I can eliminate, reduce the, of course the size of the RAM is going to be same in terms of the address 2 power n, but the into 7 bits, the number of output bits can be reduced by removing 1 address from the original design. So, this is called single qualifier. This approach is called single qualifier double address implementation. I am going to tell you a single qualifier. So, I will remove this part. Change it to a single qualifier, single address. Microprogrammed design. This is a single qualifier double address because I have a false address and a true address. I can remove one of the address and make it a single qualifier single address design, which means I can eliminate one of these 2 rows, one of these 2 columns. I can eliminate either this or this and reduce and shrink the size of the RAM, For that I need to make a minor change in the ASM. What change I will make is, I am going to remove my binary addresses, that is all I am going to do, I am not going to do anything else, because I cannot change my ASM. ASM is what I have to implement. How can I change my ASM? That is what I need to do. What I am going to do though, is to change the addresses as we know. I am going to call differently. I am going to call this address 00, S1 I am going to call 00. This one I am going to call 01. This one I am going to call 10. All I have done is, my aim is to reduce the size of the ROM has been reduced because number of address lines for a microprogram ROM is much smaller compared to a conventional traditional approach. Having done that, I want to reduce the size of the ROM in the sense of the width of the ROM, the word size. For each address, how many bits are there? In this case it is 7. I want to see if I can reduce it. That I can do by reducing one of the addresses. Instead of storing two addresses for each of the present address, I will make it only one address. That is called single qualifier, single address. But I cannot change the ASM. ASM is what I need to implement. I am going to make minor changes in the hardware, in the addressing scheme. I am going to make it 00, 01, 1011. There is some logic. There is some logic in this. It is not arbitrary. I will tell you how to do it the next time. I want to tell you how it is going to reduce the hardware. The next lecture I am going to tell you the logic behind this and also the implementation. So, what is this? Now, there is a 00 here. Now, one of the addresses, when there is a qualifier, there are no qualifiers, we need only one address. Unnecessarily we are writing two addresses. When there is no qualifier 01 or 10, we are unnecessarily reducing two addresses, writing two addresses which are both same. I can eliminate one of them. So, there is no problem about states where there is no qualifier. For states for which there is a qualifier, I want to make one of them one more than the present address. That is all I need to do. So, this state has a qualifier, A state S0 has a qualifier 10, it goes to 00 if P is true, 11 is false. So, 10 and 11. So, this is next to this, 11 is next to 10. One of the addresses has to be increment or one more than the present address, only if there is a qualifier. If there is no qualifier, that rule need not be followed. From B it goes to A 00 to 10, no problem because there is no qualifier. Similarly, from S2 to S3 there is no qualifier, so it goes from 11 to 01. But in state S3 there is a qualifier Q, one of the addresses has to be one more than 01. One more than 01 is 10, 01 is 1, 10 is 2. So, if the qualifier is true, I go back here. So, 01 becomes 10 if it is true, 01 becomes 01 when it is false. So, the rule is simple, whenever there is a qualifier, make the next address, one of the next addresses one more than the present address, the other address can be anything. When there is no qualifier, there is no such rule. So, if you make that rule very simple, my thing will change, my table will change, I will rewrite the table next time. I need not write this, there is only one address. So, I need to know what is the present address, what is the present address, what is the qualifier to be tested, or qualifier index, and what is the next address, false address, true or false bit. So, next address is but if the next address is a true address or a false address, I need to write. So, true address or a false address. So, the next address is true address or false address and the output code. So, I am going to eliminate Going to eliminate one address, next address is now only 1, not next address 2, next address false. I am going to eliminate that. I am going to increase one extra bit here. So, I may have to increase 1 bit, but then the address is more than 1 bit. Generally in this simple example itself it is 2 bits, but in general example, practical examples, addresses are large number of bits. So, there is no problem about that. But with 1 extra bit, I am able to knock off the next address. So, for the same table, for the same ASM, how to write the revised microprogram ROM table for the same ASM, how to write the revised microprogram ROM table for a single qualifier, single address mode, we will see on what is the hardware change we need to make, we need to change. So, in the next lecture what we will see is how do you write the single address, single qualifier, single address table for this example, and how do you implement it, what changes in the hardware you need to make. And after seeing that, that is a very simple thing. Then we will take one practical example of one of the problems we have defined several problems earlier. We will take one such problem and do it again. Thank you.